Hello there, and welcome to Life Beyond Seen, a place where curiosity slows its pace, where science speaks softly, and where questions are allowed to linger without demanding immediate answers. This is a space designed for listening rather than rushing, for wondering rather than concluding, and for letting the mind drift gently through ideas that are often overlooked during the louder hours of the day. Tonight's journey takes us far north, beyond familiar coastlines, beyond maps that most of us glance at without much thought, and into a place that feels both very real and strangely unreachable at the same time. We're going to talk about an ocean that exists beneath the North Pole, not a distant ocean on another planet, not a metaphorical ocean of ideas, but a real physical body of water that moves, circulates and supports life, all while being sealed beneath a shifting ceiling of ice. It is an ocean that technically belongs to Earth, yet remains largely unexplored, poorly understood, and resistant to nearly every method humans have devised to study it properly. And the question that guides us tonight is a simple one on the surface, though it becomes more complicated the longer you sit with it. Why, in an age of satellites, deep-sea robots, and constant global monitoring, can't we truly explore the hidden ocean beneath the North Pole? Before we ease into that question, take a moment to notice where you are right now. Maybe you're listening late at night with lights dimmed, or early in the morning before the day properly begins. Perhaps you're somewhere warm, wrapped in a blanket, while we talk about one of the coldest regions on the planet. Or maybe you're somewhere quiet, letting the words pass through without much effort. Wherever you are, you've arrived at this moment, and that's enough. If you find this kind of slow exploration calming, or if these topics give you a gentle sense of perspective at the end of a long day, you're always welcome to show your support in whatever small way feels right to you. This little corner of the internet exists because people enjoy lingering with questions that don't need immediate resolution, and sharing it helps others find their way here too. Now, let's begin moving north, not quickly, not dramatically, but steadily. When most people picture the North Pole, the image that comes to mind is surprisingly solid. A white expanse, endless ice, a frozen surface stretching in all directions, perhaps a flag planted heroically, or the suggestion of land hidden beneath snow. It feels fixed, like a place you could stand on and point outward from. But the North Pole in reality is nothing like that. There is no land beneath it, no rock, no soil, no permanent ground. Instead, the North Pole sits atop floating sea ice, drifting slowly over a deep ocean that never truly freezes. This fact alone already starts to complicate the idea of exploration. Humans are very good at exploring places that stay still. Mountains don't drift away while you study them. Deserts don't fracture beneath your feet and slide apart without warning. Even most oceans, vast as they are, have stable coastlines, predictable access points, and open water at the surface. The Arctic Ocean beneath the North Pole offers none of that. It is mobile, unstable, dark, and hostile in ways that don't announce themselves loudly, but persist constantly. The ice above this ocean is not a single solid sheet. It is a mosaic of ice flows, ridges, cracks, and pressure zones, all slowly moving under the influence of winds, currents, and temperature changes. Some of this ice is thin and newly formed, lasting only a season. Other sections are thicker, older, compressed over years into hard, uneven slabs. And beneath all of it lies water that remains liquid due to its salt content and the immense pressure of the ice above. This creates an environment where the boundary between surface and ocean is not clean or predictable. It shifts daily, sometimes hourly. A hole drilled through the ice one day may be completely distorted or closed the next. Equipment placed carefully can drift kilometers away without ever being touched. Even the ice itself is rarely still enough to trust for long-term installations. To truly explore an ocean, humans usually rely on access from above. Ships, submersibles, research vessels, remotely operated vehicles and sensors all depend on reaching the water's surface first. In the central Arctic, There is often no open surface to reach. The ice cover can extend hundreds of kilometres in every direction, making traditional ships nearly useless without icebreaker support. Even then, icebreakers cannot simply park and observe. They must constantly manoeuvre to avoid becoming trapped or damaged by shifting ice. There is also the matter of darkness. For much of the year, the North Pole exists under polar night, where the sun does not rise for months at a time. This darkness is not just a visual inconvenience. It affects navigation, satellite imaging, temperature regulation, and human endurance. Instruments behave differently in extreme cold. Batteries drain faster, lubricants thicken. Electronics fail in subtle, frustrating ways that don't always reveal themselves until it's too late. Underneath the ice, conditions become even more challenging. The Arctic Ocean is deep, reaching depths of over 4,000 metres in places. Pressure increases rapidly with depth, and the cold temperatures demand materials that can withstand both crushing force and freezing conditions simultaneously. Many deep-sea technologies were designed for open oceans, where retrieval and repair are difficult but possible. Under Arctic ice, recovery is often not an option. If a robot fails, it may be lost permanently, drifting under ice that no ship can reach. Communication adds another layer of difficulty. Radio signals do not travel well through seawater. GPS signals cannot penetrate ice and ocean combined. Under-ice vehicles must rely on acoustic communication, which is slow, limited in range, and easily distorted by ice movement and water layering. This means that operators often have only partial awareness of where their instruments are, what they're encountering, and whether they will return. Even mapping the seafloor beneath the North Pole is far from complete. Sonar surveys require systematic coverage, steady movement, and repeated passes to build accurate images. In the Arctic, the ice moves independently of the water below, disrupting navigation paths and rendering long-term mapping plans unreliable. A survey started in one location may end somewhere entirely different, not because of error, but because the environment itself refuses to stay aligned. Then there is the issue of time. Most polar research windows are short. Equipment must be deployed, operated, and retrieved within narrow seasonal limits. Weather can close those windows without warning. A sudden storm, shifting ice, or mechanical failure can force expeditions to abort plans after years of preparation. Unlike research in more forgiving environments, Arctic missions rarely allow for improvisation once conditions turn unfavourable. Human presence itself becomes a limiting factor. Extended exposure to extreme cold affects concentration, motor control, and decision-making. Simple tasks take longer. Mistakes become more likely. Fatigue sets in quietly. Even with modern protective gear, humans are not designed to operate comfortably in such conditions for long periods. Every additional day in the high Arctic increases risk, cost, and strain on both people and equipment. Because of all this, much of what we know about the Arctic Ocean comes indirectly. From satellite data that infer conditions rather than observe them directly. From drifting buoys that provide isolated measurements. From brief sampling campaigns that offer snapshots rather than continuous records. These methods are valuable, but they do not replace sustained exploration. They tell us something is happening, but not always why, how, or what it means in detail. There is also a quiet misconception that exploration is simply a matter of effort or funding. That if we wanted to explore the hidden ocean beneath the North Pole badly enough, we would have done it by now. The reality is less about willingness and more about physics. Ice does not negotiate. Pressure does not compromise. Cold does not ease up because a research proposal was approved. The environment sets the terms, and those terms are strict. And yet, this hidden ocean matters more than its obscurity might suggest. It plays a role in regulating Earth's climate. It stores heat, circulates nutrients, and interacts constantly with the ice above it. Changes in this ocean influence ice thickness, global ocean currents, and weather patterns far beyond the Arctic itself. What happens beneath the North Pole does not stay there. It connects quietly to systems that affect the entire planet. This makes the difficulty of exploration feel slightly unsettling. There is something important happening in a place we cannot easily reach, observe, or understand in real time. We rely on models, assumptions, and limited data, knowing that large gaps remain. Not because of neglect, but because access itself is constrained by forces we cannot override. As we continue, we'll take a closer look at why the North Pole is often misunderstood as a fixed place, how the ice above the ocean behaves in ways that actively resist study, and why even our most advanced tools struggle in this environment. We'll move gradually from the surface down, from what we imagine to what actually exists, following the quiet complexity of a region that refuses to be simplified. For now, let that image settle. Not a frozen cap at the top of the world, but a restless ocean sealed beneath moving ice, waiting not to be conquered, but simply observed. And even that, as it turns out, is asking a great deal. When people think about the North Pole, they usually picture something firm and definite, a place you could stand on if you were brave enough or warm enough. The mental image is often borrowed from maps, cartoons, globes, and stories told since childhood. A white cap at the top of the world, a fixed point, a destination, something like land, only colder. That image is comforting because it fits neatly into how we like to understand geography. Continents are solid, poles are points, oceans are separate things. But the North Pole quietly refuses to follow that logic. The first thing that unsettles this picture is the simple fact that the North Pole is not land at all. There is no continent beneath it, no hidden island waiting under the ice, no rocky foundation anchoring it in place. The North Pole exists above open ocean, specifically the Arctic Ocean, and the ice at the surface is floating. This means the North Pole is not a fixed location in the physical sense we usually mean. It is a set of coordinates that drift over water that is constantly in motion. That alone changes the meaning of the place. You cannot build a permanent structure there in the way you might at the South Pole, which sits on a massive continental ice sheet covering Antarctica. You cannot rely on the ground staying where it is. Any camp, station or marker placed at the North Pole begins drifting the moment it is set down. Some drift slowly, others accelerate depending on winds and currents. Over days or weeks, a location that was once the pole may end up many kilometers away. This drifting nature makes the North Pole feel less like a destination and more like a moment. You arrive, you acknowledge where you are, and then the environment carries you onward whether you want it to or not. Exploration thrives on stability, on repeatability, on the ability to return to the same place and compare results. The North Pole offers none of that. Even returning to the same coordinates does not guarantee you will encounter the same conditions. The ice itself adds another layer of misunderstanding. Many people imagine Arctic ice as a smooth, flat sheet, like a frozen lake extending endlessly. In reality, the surface is chaotic. Ice flows collide, pile up, fracture, refreeze, and buckle. Pressure ridges rise like frozen waves. Leads, which are cracks of open water, can open and close unpredictably. Snow hides weak spots. What looks solid from a distance may be thin or newly formed. What looks dangerous may be thick and stable. There is no consistent pattern that can be trusted for long. Underneath this surface chaos is water that never fully rests. Currents move heat from lower latitudes into the Arctic. Layers of water with different temperatures and salinities slide past one another. Warmer Atlantic water flows beneath colder surface layers, slowly melting the ice from below. This process is invisible from above but profoundly important. It means the ice is being reshaped constantly, even during the coldest months. Because the ice floats, it responds quickly to changes in wind. A strong storm can compress ice in one region, making it thicker and more difficult to penetrate, while pulling it apart elsewhere, creating wide stretches of open water. These changes can happen over hours, not seasons. Planning around them is more like trying to schedule research on a moving puzzle. than on a stable platform. Another misconception is that the North Pole is the coldest place in the Arctic. While it is certainly cold, coastal regions and parts of Siberia can experience much lower temperatures. The Arctic Ocean, insulated by water beneath the ice, can actually be more thermally stable than exposed land. This does not make it gentle, but it does make it different. Cold at the North Pole is persistent rather than extreme, relentless rather than dramatic. It wears things down slowly rather than shattering them all at once. This subtlety is part of what makes the region difficult to understand from afar. The dangers are not always obvious. Ice does not announce when it is about to shift. Pressure ridges form quietly. Flows separate without warning. An area that was safe to walk across in the morning may be broken by afternoon. For humans used to reading landscapes, this lack of visual cues is deeply unsettling. Navigation suffers as well. Traditional landmarks do not exist. There are no mountains, trees or coastlines to orient yourself by. Everything looks the same in every direction, especially during overcast conditions or polar night. Compasses become unreliable near the magnetic pole, which itself is not located at the geographic North Pole and moves over time. GPS works at the surface but loses usefulness under ice. Even experienced polar travellers describe the region as disorienting, a place where distance and direction feel abstract. From above, satellites provide a broad view, but even they are limited. Ice thickness is difficult to measure accurately over large areas. Surface features can be misleading. A region that appears stable may be thin. A dark patch might indicate open water or simply snow conditions. Satellites pass overhead at intervals, offering snapshots rather than continuous observation. Between those snapshots, the ice can change dramatically. This gap between appearance and reality contributes to the persistent myth that the North Pole is more accessible than it truly is. It looks simple on a map, a point at the top, but maps flatten complexity. They hide motion. They imply permanence where none exists. They make it easy to forget that the pole is not a thing you arrive at so much as a coordinate you briefly occupy. There is also a cultural layer to this misunderstanding. For centuries, the North Pole has been framed as a prize, a final blank space to be claimed. Explorers race to reach it, planting flags, taking photographs, and leaving markers. These expeditions reinforce the idea of the pole as a place of arrival rather than a system in motion. The language of conquest stuck, even as the reality quietly contradicted it. Modern science approaches the region differently, but it still inherits some of these assumptions. Research proposals often begin with the idea of studying the North Pole as if it were a stable field site. In practice, scientists must adapt to a moving target. Instruments drift. Sampling locations change. Data sets become patchworks rather than continuous lines. The work becomes less about controlling variables and more about accounting for constant change. This has consequences for what we can know. Long-term measurements are difficult. Repeating experiments under identical conditions is nearly impossible. Separating short-term variability from long-term trends becomes a challenge when the environment itself refuses to hold still. Scientists compensate with statistical models, indirect measurements, and cross-referencing data from multiple sources, but uncertainty remains. Even the idea of depth behaves differently here. In most oceans, depth is measured from a stable surface. In the Arctic, the surface itself moves up and down with ice thickness, snow accumulation, and pressure ridges. This affects how instruments are calibrated and how data is interpreted. A sensor suspended beneath ice must constantly adjust to changes above it, and those adjustments introduce error. The North Pole is also quieter than people expect. There is no crashing surf, no constant roar. Sound behaves strangely under ice, travelling long distances through water and solid ice alike. This creates an acoustic environment that is difficult to interpret. Natural sounds blend with the noise of cracking ice and distant movement. For researchers using sound to map or communicate, this complexity adds another obstacle. All of this leads to a simple but uncomfortable truth. The North Pole resists simplification. It is not a static point, not a frozen cap, not a place that can be neatly pinned down. It is a dynamic system, one that shifts constantly and does not prioritize human convenience. Our mental images lag behind reality, shaped by outdated maps and simplified narratives. This mismatch between imagination and reality matters because it affects expectations. When people ask why we haven't explored the ocean beneath the North Pole more thoroughly, they often imagine it as a straightforward extension of deep-sea exploration elsewhere. Drill a hole, send down a robot, gather data. But that sequence assumes a stable surface, predictable conditions and reliable access. None of those assumptions hold here. Instead, every attempt to study the region must first contend with the fact that the ground beneath your feet is not ground at all, and it will not stay where you left it. Every piece of equipment must be prepared not just for cold and pressure, but for motion, distortion, and loss. Every plan must include the possibility that the environment will quietly undo it. As we move forward, it becomes important to keep this corrected image in mind. Not a frozen monument at the top of the world, but a restless, drifting surface concealing a deep ocean below. An environment defined less by extremes than by instability. This instability is not a flaw or an anomaly. It is the defining feature of the place. Understanding that is the first step toward understanding why the hidden ocean beneath the North Pole remains so difficult to explore. And it sets the stage for looking more closely at what lies beneath the ice itself, where motion continues, unseen, and where the challenges only deepen as we move downward. Beneath the drifting ice of the North Pole lies an ocean that is easy to forget precisely because it is so thoroughly concealed. Cold and darkness do not merely sit on top of it as surface conditions. They seep into every layer of interaction humans have with this place. They shape how the ocean behaves, how life survives within it, and how difficult it becomes for us to observe anything directly. This is not an ocean hidden in the dramatic sense, like a lost city waiting to be revealed. It is hidden in a quieter way, obscured by physical barriers that rarely relent, and environmental conditions that actively interfere with perception. Cold here is not just a number on a thermometer. It is a constant influence that alters materials, slows reactions, and changes how energy moves. Seawater beneath the North Pole hovers near its freezing point, but because of its salinity, it remains liquid even at temperatures that would turn fresh water into solid ice. This creates a delicate balance. Slight changes in temperature or salinity can shift layers of water, alter currents, and influence how heat is exchanged between ocean and ice. These processes happen continuously, but they do not announce themselves. They occur in darkness, under pressure, far from any human senses. Darkness is perhaps the more deceptive barrier. For much of the year, sunlight barely penetrates the Arctic Ocean, and during polar night it disappears entirely. Even when the sun does rise, its angle is low, and thick ice and snow scatter what little light reaches the surface. By the time you move a few meters below the ice, natural light is effectively gone. Exploration becomes an exercise in artificial illumination, which brings its own complications. Light behaves differently in cold, particulate-rich water. It scatters. It reflects off ice crystals suspended in the water column. It creates glare and shadows that distort perception. Cameras struggle to capture clear images. Colours shift. Depth becomes difficult to judge. What looks like open water may be a wall of ice. What looks like a solid surface may be a thin layer ready to fracture. Even high-quality optical systems provide only a narrow, localized view, offering fragments rather than a coherent picture. Sound, often used as an alternative to light, is also affected. Acoustic signals bounce off the underside of ice in unpredictable ways. Temperature gradients in the water bend sound paths, creating echoes that confuse interpretation. The very structure of the ice underside, rough and uneven, scatters sound rather than reflecting it cleanly. This makes sonar mapping less precise than it would be in open ocean environments. What should be a clean outline of the seafloor becomes a blurred suggestion. Cold also affects the ocean's chemistry. Gas solubility changes. Oxygen levels vary with temperature and ice cover. Nutrients move slowly, constrained by limited mixing and seasonal cycles. These chemical gradients influence where life can exist and how active it can be. But measuring them requires instruments that can survive long deployments without maintenance, often for months or years at a time. Cold shortens the lifespan of sensors, calibration drifts, small errors accumulate, and retrieving instruments for adjustment is rarely straightforward. The darkness complicates biological study in particular. Much of what we know about marine ecosystems comes from visual observation. We watch how organisms move, interact, feed, and respond to changes. Beneath the North Pole, this approach is largely unavailable. Many organisms are adapted to low light or no light conditions. Some rely on chemical cues rather than vision. Others migrate vertically in response to subtle changes in light or temperature that are difficult to detect externally. Sampling life in this environment is challenging not only because of access, but because disturbance itself can alter behaviour. Artificial lights can attract or repel organisms. Noise can disrupt normal patterns. Even the presence of a research vehicle changes the local environment enough to skew observations. Scientists must constantly ask whether what they are seeing is representative or simply a reaction to intrusion. There is also the issue of scale. The Arctic Ocean is not uniform. Conditions beneath the North Pole differ from those closer to continental shelves or open water. Ice thickness varies. Water masses mix differently. Local currents create pockets of relative stability or turbulence. Darkness and cold are constant themes, but their effects are not evenly distributed. A measurement taken in one location cannot be easily generalized to another, even if they appear similar on a map. Time behaves differently here as well. Seasonal cycles are extreme. Months of darkness are followed by months of continuous daylight, and these shifts influence everything from ice growth to biological productivity. The ocean responds slowly, storing heat and releasing it gradually. Processes overlap. Cause and effect are separated by long delays. Understanding these dynamics requires long-term observation, but long-term observation is precisely what is hardest to achieve. Cold interferes with power. Batteries lose capacity. Solar power is unreliable for much of the year. Nuclear options are limited and heavily regulated. This constrains how long instruments can operate autonomously. Data storage becomes a concern. Transmission is slow and intermittent. Scientists often recover data months or years after it was collected, long after the conditions that produced it have changed. Darkness also affects human decision-making. Working without visual cues increases cognitive load. Fatigue sets in faster. Errors become more likely. Under-ice operations require careful planning and redundancy, but even then, unexpected conditions can force abrupt changes. A vehicle might lose orientation. A tether might snag on ice. A signal might drop out without warning. In an environment where recovery is uncertain, each of these risks carries weight. Even defining what it means to explore this ocean becomes complicated. In many contexts, exploration implies movement, mapping, and discovery through direct observation. Here, exploration often looks like indirect inference. Temperature profiles, salinity measurements, acoustic signals interpreted through models, sparse biological samples. Each piece adds to a growing but incomplete picture. The ocean remains present but partially obscured, like a conversation heard through a wall. There is a temptation to frame this hiddenness as a technological problem waiting to be solved. Better robots, stronger materials, smarter sensors. And while progress is constant, the environment continues to impose fundamental limits. Ice blocks access. Cold degrades systems. Darkness removes context. These are not obstacles that can be eliminated, only managed imperfectly. The ocean beneath the North Pole is not passive in this relationship. It is not simply waiting to be revealed. Its properties actively shape the terms of engagement. Heat moves upward, melting ice from below. Fresh water from melting ice alters surface layers. Salt rejection during ice formation increases density and drives circulation. These processes are subtle but powerful, and they operate continuously, regardless of whether anyone is watching. This hidden ocean also interacts with the global system in ways that are easy to underestimate. It influences deep water formation, which feeds into global circulation patterns. It stores carbon. It affects atmospheric conditions by regulating ice cover and heat exchange. Understanding these roles requires knowing not just surface conditions but what happens below, in the cold and dark layers that are hardest to access. The lack of visibility has consequences for public perception as well. What cannot be seen is easy to ignore. Satellite images show shrinking ice extent, but they do not show what happens beneath. Changes in ocean heat content, circulation, and ecosystem structure remain abstract. Without direct imagery or narratives, the hidden ocean remains out of sight and often out of mind. Yet for scientists working in this field, the lack of visibility does not diminish importance, it heightens it. Every dataset represents effort under difficult conditions. Every successful deployment is a negotiation with cold and darkness. Every failure is a reminder that the environment sets the rules. Progress is measured not in dramatic breakthroughs, but in incremental understanding. This is why exploration here feels slower, more tentative, and less complete than elsewhere. It is not for lack of curiosity or capability. It is because cold and darkness impose constraints that ripple through every aspect of research. They limit access, distort perception, and demand patience. As we continue, it becomes clear that the ocean's concealment is not accidental. It is the product of physical processes that reinforce one another. Ice blocks light. Cold preserves ice. Darkness slows biological activity and observation alike. Together, they create a system that resists intrusion not through force, but through persistence. Understanding this helps explain why the hidden ocean beneath the North Pole remains one of Earth's least explored environments. And it prepares us to look more closely at the ice itself, not just as a surface barrier, but as a dynamic, moving structure that complicates exploration in ways that go beyond cold and darkness alone. Ice at the North Pole is often spoken about as if it were a static lid, a frozen ceiling sealing the ocean below in place. The language we use encourages that assumption. Ice cover, ice cap, frozen surface. Each phrase suggests something solid, stable, and dependable. Something that stays where it is once it forms. But the reality is far less accommodating. The ice above the hidden Arctic Ocean is not still. It does not rest. It moves constantly, quietly, and with a persistence that reshapes everything beneath and above it. This movement is not dramatic most of the time. There are no roaring avalanches or crashing waves to announce it. Instead, the ice shifts in slow, grinding motions driven by wind, currents, and the Earth's rotation. Flows slide past one another. Plates rotate, cracks open, widen, narrow, and sometimes disappear entirely. Pressure builds invisibly until it releases, forcing slabs of ice upward into jagged ridges or downward into the water. The entire surface behaves less like a frozen lake and more like a crowded traffic system with no lanes, no signals, and no predictable rules. One of the most difficult things to internalize is that Arctic sea ice is not a single sheet. It is a patchwork of individual pieces, each with its own thickness, age, and history. Some ice forms in a single winter and melts the following summer. Other sections survive multiple seasons, becoming thicker and denser over time. These older pieces, known as multi-year ice, are harder, rougher, and more resistant to melting. They also behave differently under stress, cracking less easily, but exerting greater force when they collide with other flows. Wind plays a dominant role in this motion. Because the ice floats, it responds readily to surface winds, often moving faster than the water beneath it. A sustained wind can push ice across vast distances, compressing it against other flows or coastlines, or pulling it apart to create open leads of water. These leads can appear rapidly, exposing the ocean below, only to refreeze days or even hours later. For researchers, this means access points open and close without warning, and what was a safe platform can suddenly become fragmented. Currents add another layer of complexity. Ocean currents beneath the ice move more slowly than winds, but their influence is steady and persistent. They transport heat, salt, and momentum, subtly shaping how ice forms and melts from below. In some regions, warmer water erodes the ice underside, thinning it invisibly until it becomes fragile. From above, the ice may look intact, but its structural integrity has already been compromised. The interaction between wind-driven ice motion and current-driven water movement creates shear zones, areas where ice moves at different speeds or directions over short distances. These zones are prone to cracking. They're also difficult to predict. Instruments placed across a shear zone may be torn apart as ice pulls in opposite directions. Tethers snap. Cables stretch and fail. Carefully planned arrays become scattered debris fields beneath the ice. Cracking itself is not a singular event. It is a process. Stress accumulates slowly as ice is pushed and pulled. Microfractures form long before visible cracks appear. These fractures weaken the ice internally, creating planes of failure that can activate suddenly. When a crack finally opens, it may do so silently, or with a deep, resonant sound that travels through the ice and water alike. Either way, the result is a sudden reorganization of the surface. From an exploration standpoint, this instability is relentless. A research camp established on ice is never truly secure. Scientists monitor crack formation constantly, listening for changes, watching for subtle shifts. Even so, camps have been lost when ice broke apart unexpectedly. Equipment has drifted away. Evacuations have been required with little notice. These are not rare occurrences. They're accepted risks of working in an environment that refuses to settle. Ice thickness adds to the challenge. Thickness varies dramatically over short distances. A snow-covered surface can hide thin ice beneath. Pressure ridges may contain ice tens of meters thick, formed by slabs forced upward and downward during collisions. Drilling through such ridges requires time, energy, and heavy equipment, all of which must be transported across unstable terrain. Choosing where to drill becomes a gamble informed by experience rather than certainty. Even measuring thickness accurately is difficult. Radar and electromagnetic sensors provide estimates, but they have limitations. Snow cover interferes with signals. Salinity affects readings. Ground truth measurements require physical drilling, which is slow and spatially limited. As a result, maps of ice thickness are approximations, useful but incomplete. They cannot capture the rapid changes caused by storms or shifts in wind patterns. The ice also responds to temperature in non-linear ways. Small increases in air temperature can lead to disproportionate melting, especially when combined with warm water below. Meltwater pools form on the surface during summer, absorbing more sunlight and accelerating melting. These pools drain through cracks, delivering fresh water into the ocean and altering local chemistry. They also weaken the ice mechanically, making it more prone to fracture later. Seasonal cycles do not bring rest either. In winter, ice grows thicker, but it also becomes more brittle. Extreme cold increases internal stress. In summer, ice thins and softens, becoming more flexible but also more vulnerable. The transition seasons, spring and autumn, are particularly unpredictable. Freeze up and break up involve rapid changes that challenge even experienced observers. For exploration technologies, this constant motion is a fundamental problem. Instruments designed to remain stationary are rarely stationary for long. Moorings drift. Anchors embedded in ice move with the flow they are attached to. Long-term experiments require constant recalibration as reference points shift. This complicates data interpretation, especially when trying to detect subtle trends over time. Autonomous vehicles face similar issues. An underwater robot navigating beneath ice must account for the fact that its ceiling is moving. A map created at one moment may be inaccurate the next. Docking stations placed under ice can drift away from expected locations. Navigation systems relying on fixed coordinates become unreliable when the environment itself is in motion. Recovery becomes a major concern. In open water, a failed instrument can often be retrieved later by returning to its last known position. Under drifting ice, that position may no longer exist. The ice above may have moved tens or hundreds of kilometers, leads may have closed, new ridges may block access. Instruments can be lost not because they failed, but because the surface conditions above them changed. This motion also complicates safety planning. Emergency evacuation routes cannot be assumed to remain open. Helicopter landing zones may fracture. Ice runways may become uneven or unstable. Logistics must remain flexible, with contingency plans layered upon contingency plans. Every decision carries the understanding that the environment may change before it can be executed. Beyond the practical challenges, there is a conceptual shift required to understand ice that never rests. It forces a departure from land-based thinking. On land, stability is assumed unless disrupted. In the Arctic, motion is assumed unless briefly paused. This inversion affects how research questions are framed, how experiments are designed, and how success is measured. The ice is not simply an obstacle to be overcome, it is an active participant in the system being studied. Its movement influences ocean circulation, mixing water layers and redistributing heat. Cracks allow gas exchange between ocean and atmosphere. Pressure ridges alter habitat structure beneath the ice, creating refuges and barriers for marine life. Ignoring ice dynamics leads to incomplete understanding. This is why truly exploring the ocean beneath the North Pole cannot be separated from understanding the ice above it. The two are inseparable. Any attempt to treat the ice as a static platform quickly runs into problems. The ice does not accommodate fixed plans. It responds to forces beyond human control, following patterns that emerge from physics rather than intention. Over time, climate change has altered these dynamics further. The proportion of multi-year ice has declined. Thinner ice moves faster and responds more quickly to wind. Cracks form more readily. The surface becomes more dynamic, not less. This increased mobility makes exploration even more challenging despite advances in technology. A thinner, more fragile ice cover is not easier to work on. It is more unpredictable. This reality challenges a common assumption that diminishing ice automatically improves access to the Arctic Ocean. While open water seasons have expanded in some regions, the central Arctic, including the North Pole, remains ice-covered for most of the year. And thinner ice, while easier to break through in theory, offers less stability for operations. The risks change rather than disappear. Understanding ice as a restless medium helps explain why progress beneath it is slow and uneven. It is not a matter of reaching a destination and beginning work. It is a matter of constantly adapting to a surface that refuses to stay still long enough to be taken for granted. Every observation is provisional. Every measurement is contextual. Every success is temporary. As we continue deeper into the reasons exploration remains limited, this restless ice becomes a recurring theme. It interferes with satellites, disrupts machinery, and reshapes access in ways that ripple through every layer of effort. And while it may appear silent and still from afar, up close, it reveals itself as one of the most dynamic, unforgiving environments on Earth. With that in mind, the next challenge becomes clearer. Even if we could somehow freeze the ice in place, even if it stopped moving long enough to provide a stable surface, much of what we rely on to explore from above would still fall short. Because the difficulties do not end at the surface. They extend upward, into orbit, and into the limits of what our distant eyes can truly see. From far above the Earth, satellites give the impression of omniscience. They glide silently through orbit, scanning continents, oceans, storms, forests and ice, with instruments sensitive enough to detect temperature differences smaller than a single degree. They track ships across seas, measure sea level rise to millimeters, and map ice cover across the entire Arctic in near real time. It's easy, from this vantage point, to assume that if something exists on our planet, satellites must be able to see it. And yet, when it comes to the ocean hidden beneath the North Pole, satellites reach a hard and unavoidable limit. The first misconception lies in what satellites actually observe. Despite the clarity of the images they produce, satellites do not see objects directly in the way human eyes do. They detect signals, reflected sunlight, emitted heat, microwave radiation, variations in gravity. Each measurement is an interpretation of how energy interacts with matter at or near the surface. Satellites excel at surfaces. They struggle profoundly with depth. Ice is the primary barrier. Thick Arctic sea, ice blocks most forms of electromagnetic radiation. Visible light does not pass through more than a few centimeters of snow-covered ice. Infrared radiation, which satellites use to measure temperature, only reflects information about the surface. Microwave sensors can penetrate snow and thin ice to a degree, but their reach is shallow and their resolution coarse. They provide estimates of ice thickness, not windows into the ocean below. Even the most advanced radar systems are limited. Radar waves interact strongly with ice, scattering and reflecting in complex ways that obscure deeper layers. What returns to the satellite is a noisy signal dominated by surface roughness, snow properties, and ice structure. Extracting meaningful information about what lies beneath requires assumptions and models that introduce uncertainty. The deeper you try to look, the less reliable the signal becomes. Water itself is another obstacle. Seawater absorbs electromagnetic radiation efficiently. This is why the ocean appears dark from space beyond its surface reflection. Most satellite sensors simply cannot penetrate water at all. Those that can, such as certain optical sensors, are limited to very shallow depths in clear, sunlit conditions. The Arctic Ocean beneath the North Pole offers neither clarity nor light. Darkness and ice render optical penetration essentially non-existent. Gravimetric satellites offer a more indirect approach. By measuring tiny variations in Earth's gravitational field, they can infer the distribution of mass beneath the surface. This method has been used to map large-scale features like ocean basins and tectonic structures. However, its resolution is low. It cannot resolve fine details of seafloor topography or water movement beneath ice. It tells us something is there, not what it is doing. Altimetry satellites, which measure surface height with remarkable precision, can infer changes in sea level and ice thickness over time. They are invaluable for tracking trends, but again, they observe the interface, not the interior. A change in ice height might reflect melting from below, snow accumulation from above, or compaction within the ice itself. Disentangling these processes requires complementary data from below the surface. Satellites also struggle with temporal continuity in the Arctic. Orbits determine when and how often a satellite passes over a given location. While coverage is frequent, it is not continuous. Between passes, conditions can change significantly. Ice can drift. Cracks can open or close. Storms can reshape the surface. The ocean beneath responds on its own timescales. Satellites capture moments, not processes. Cloud cover adds another layer of interference. While some sensors can see through clouds, others cannot. Optical imagery is often unavailable during polar night or persistent cloudiness. This limits the ability to cross-reference different types of data. When gaps appear, scientists must interpolate, relying on models rather than observation. There is also the challenge of resolution. Satellites balance coverage and detail. Instruments designed to observe large areas sacrifice fine resolution. Those capable of finer detail cover smaller swaths and require longer times to build a complete picture. The Arctic Ocean beneath the North Pole is vast. Mapping it comprehensively at high resolution from space is not currently feasible. Even when satellites detect signals related to subsurface processes, interpretation is indirect. For example, changes in ice motion can suggest shifts in ocean currents below. Variations in ice thickness may hint at heat transport from beneath. But these are inferences, not observations. Multiple explanations can fit the same surface signal. Without direct measurements from the ocean itself, certainty remains elusive. This reliance on inference is not a flaw in satellite technology. It is a reflection of physical limits. Electromagnetic waves interact with matter in predictable ways, and ice and seawater are highly effective barriers. No amount of computational power can extract information that never reaches the sensor. Satellites are constrained by physics as much as by engineering. There is also the issue of scale mismatch. Many critical processes beneath the North Pole occur at scales too small or too transient to be detected from orbit. Turbulence, microcurrents, biological interactions, chemical gradients. These phenomena influence the system profoundly, but they leave little surface signature. They happen quietly, locally, and often below the threshold of satellite detection. The underside of sea ice itself is particularly elusive. Its structure affects heat exchange, habitat availability, and nutrient flow. Yet satellites cannot see it. They cannot resolve the ridges, channels, and cavities that form beneath ice flows. These features shape the ocean environment in ways that are invisible from above. Attempts to combine satellite data with models help bridge some gaps. Numerical simulations use surface observations as boundary conditions to estimate subsurface behavior. These models are powerful and improving, but they depend on assumptions and parameterizations. Without sufficient ground truth, models risk reinforcing their own biases. Satellites provide constraints, not answers. The remoteness of the North Pole amplifies these challenges. Unlike coastal regions where satellite data can be validated against ships, buoys, and fixed stations, the Central Arctic has few permanent reference points. Drifting buoys help, but they are sparse and vulnerable to loss. Subsurface moorings are difficult to maintain. The feedback loop between observation and validation is weak. There is also a psychological dimension to satellite imagery. High-resolution images give a sense of mastery. They flatten complexity into something comprehensible. Ice extent maps, colour-coded and animated, suggest clarity. But this clarity is selective. It emphasises what can be measured easily and downplays what cannot. The hidden ocean remains hidden not because it is unimportant, but because it resists these modes of observation. This can influence funding priorities and public understanding. When surface changes are visible, they attract attention. When subsurface changes are inferred or uncertain, they are easier to overlook. Yet the ocean beneath the ice plays a critical role in driving those visible changes. Heat stored below determines how ice melts above. Currents transport energy and nutrients across vast distances. Ignoring the hidden component risks misunderstanding the whole. Satellites are indispensable. Without them, our understanding of the Arctic would be far poorer. They provide context, continuity, and global perspective, but they are not explorers in the traditional sense. They do not venture into the depths. They do not adapt to local conditions. They do not experience the environment they observe. They watch from afar, limited by the signals that reach them. This limitation becomes especially stark at the North Pole, where ice, darkness, and depth conspire to block nearly every direct line of sight. Satellites tell us where the ice is, how it moves, how it changes over time. They hint at what might be happening below, but they cannot confirm it. They cannot replace the need for instruments in the water, feeling the currents, measuring temperature directly, sampling chemistry, encountering life. Understanding this helps reframe the question of why the hidden ocean remains unexplored. It is not because we lack eyes in the sky. It is because eyes in the sky are the wrong tool for seeing through ice and into darkness. Exploration here demands presence. however limited and risky that presence may be. As we move forward, this gap between surface observation and subsurface reality becomes more pronounced. The limitations of satellites push us toward machines that must operate where signals fade and conditions intensify. And those machines, as it turns out, face challenges of their own, shaped not by distance from Earth, but by proximity to one of its most unforgiving environments. Beneath the drifting ice and the layers of cold, dark water, another force asserts itself quietly and relentlessly. It does not announce its presence with motion or sound, and it does not change quickly enough to be dramatic, yet it shapes everything that happens in the deep Arctic Ocean. Pressure. Constant crushing pressure that increases meter by meter, indifferent to technology, intention, or effort. At the surface, pressure is something we rarely think about. Air presses down on us all the time, but our bodies are adapted to it so completely that it fades into the background. Even a few meters underwater, pressure begins to make itself known. Ears need to equalize. Movements feel heavier. At greater depths, the environment becomes utterly alien to human physiology. In the Arctic Ocean beneath the North Pole, this transition happens beneath an ice ceiling that already limits escape, light, and communication. Water is dense. For every 10 meters you descend, pressure increases by roughly 1 atmosphere. That means that at a depth of 1,000 meters, the pressure is about 100 times what we experience at the surface. In parts of the Arctic Ocean where depths exceed 4,000 meters, pressure climbs to levels that would crush unprotected equipment instantly. Metal deforms, seals fail, microscopic flaws become catastrophic weaknesses. This pressure does not exist in isolation. It acts in combination with near-freezing temperatures and complete darkness. Materials behave differently when cold. They become brittle. Elastic components lose flexibility. Lubricants thicken or solidify. Combine that with immense external force pressing inward from every direction, and the margin for error shrinks dramatically. Designing equipment to survive these conditions is not simply a matter of making things stronger. Strength adds weight. Weight complicates deployment through ice. Larger structures are harder to maneuver under drifting flows. Pressure-resistant housings must be perfectly sealed, often spherical to distribute force evenly. Even then, seals must endure not only pressure, but repeated thermal cycling as instruments move through layers of varying temperature. In open ocean exploration, deep-sea submersibles often rely on support ships directly above. If something goes wrong, recovery, while difficult, is at least theoretically possible. In the Central Arctic, recovery is uncertain at best. Ice blocks direct vertical access. A vehicle lost to pressure failure or structural compromise may never be retrieved. This raises the stakes for every deployment. Each mission must assume that failure could be permanent. Pressure also limits the types of sensors that can be used. Delicate instruments that work well in shallower environments may not survive long at depth. Components must be miniaturized and reinforced. Calibration becomes more difficult as pressure affects sensor response. Even when instruments survive physically, their data may drift subtly as pressure alters internal properties. These shifts are small but significant, especially when measuring slow, long-term processes. The human inability to directly experience these depths adds another layer of complexity. Unlike surface or shallow water research, deep Arctic exploration is entirely mediated through machines. There are no divers, no direct observations. Everything we know comes through layers of interpretation. A pressure sensor reports a number. A temperature probe reports another. A camera sends back images illuminated by artificial light. Each data point is filtered through technology designed to withstand conditions humans cannot. Pressure also influences the ocean itself. Water density increases with depth, shaping stratification and circulation. In the Arctic, this stratification is particularly complex. Cold, Relatively fresh water sits above warmer, saltier layers originating from lower latitudes. Pressure helps maintain these layers, limiting vertical mixing. Heat can be trapped below, slowly eroding ice from beneath without ever reaching the surface in obvious ways. Understanding these pressure-driven dynamics requires measurements across depth, but deploying instruments at multiple depths beneath moving ice is extremely challenging. Moorings must be anchored to the seafloor, extending upward through kilometers of water. They must flex without breaking as ice above drifts. Lines must withstand tension from currents and ice motion while resisting compression and abrasion. Each additional sensor increases the risk of failure somewhere along the system. Pressure also affects sound, one of the primary tools used for under-ice navigation and mapping. Sound speed varies with pressure, temperature, and salinity. In the Arctic, these variables change rapidly with depth. Sound waves bend, refract, and scatter, complicating interpretation. A sonar return may reflect not from the seafloor, but from a layer boundary or an ice keel above. Distinguishing signal from artifact becomes a constant challenge. The crushing force at depth also constrains exploration timelines. Pressure fatigue accumulates in materials over time. Repeated deployments weaken structures. Microfractures grow. What survives one mission may fail on the next. This limits how often equipment can be reused and increases costs. In a region where logistics are already expensive and seasonal, this adds another barrier to sustained study. There is also the issue of unpredictability. Pressure at depth is constant, but its interaction with moving ice and currents introduces dynamic stresses. A vehicle navigating under ice may encounter vertical motion as water layers shift. These movements impose additional loads. A tethered instrument may experience sudden tension changes as ice above moves. Designing for worst-case scenarios becomes essential, but worst cases are difficult to define in such a variable environment. Biological exploration is shaped by pressure as well. Organisms living at these depths are adapted to it. Their cellular structures, enzymes, and membranes function under conditions that would destroy surface life. Studying these organisms requires bringing samples to the surface without killing them or altering their structure. Pressure changes during retrieval can be lethal. Specialized pressure-retaining samplers exist, but they are complex, heavy, and prone to failure. Because of this, much of the deep Arctic biosphere remains inferred rather than observed. We detect DNA fragments, we analyze chemical signatures, we infer metabolic processes. Direct observation of living organisms at depth beneath the North Pole is rare. Pressure makes the act of bringing the deep ocean into the laboratory fundamentally disruptive. The psychological effect of pressure on planning cannot be ignored either. Engineers and scientists know that failure modes multiply with depth. This knowledge encourages caution. Missions are designed conservatively. Risks are minimized. Ambitious plans are scaled back. While this is sensible, it slows progress. Each step forward is measured, tested, and often delayed. Pressure also intersects with another constraint that becomes increasingly severe as depth increases: time. The deeper an instrument goes, the longer it takes to deploy and retrieve. In the Arctic, deployment windows are short. Weather changes quickly. Ice conditions shift. A delay at depth can cascade into missed recovery opportunities at the surface. Pressure forces patience, but the environment rarely offers it. All of this contributes to a situation where the deepest parts of the Arctic Ocean beneath the North Pole are among the least directly explored regions of Earth's oceans. Not because they are uniquely deep compared to other ocean basins, but because reaching them requires overcoming pressure without the usual support systems available elsewhere. It is tempting to imagine that pressure is a solved problem, something engineers have mastered through decades of deep-sea exploration. In many contexts that is partly true, but the Arctic adds layers of complication that reintroduce uncertainty. Pressure-resistant technology designed for open oceans must be adapted for cold, ice-covered conditions. Every adaptation introduces new variables, Every variable introduces risk. This is why the crushing pressure of polar depths is not just a background condition. It is an active participant in limiting exploration. It shapes technology, constrains methods, and enforces caution. It turns the deep Arctic Ocean into a place where presence is mediated, fragile, and often fleeting. As we move on, it becomes clear that even when machines survive the pressure, even when they withstand cold and darkness, they face another persistent challenge. They must operate in an environment that refuses to stay still, where navigation is uncertain and reference points vanish. Pressure is only one part of a system that tests every assumption we bring with us. When humans cannot go somewhere themselves, they send machines. That logic has guided exploration for centuries, from telescopes peering into space to probes descending into deep oceans. In theory, machines should be perfect for the hidden ocean beneath the North Pole. They do not feel cold. They do not panic in darkness. They do not need oxygen. And yet, in practice, machines struggle here in ways that are both subtle and severe. They freeze, they drift, and sometimes they simply vanish, leaving behind incomplete data and unanswered questions. Cold is the first adversary, and it works slowly. Electronics generate heat when they operate, but in the Arctic that heat is quickly drawn away. Components cool unevenly. Circuit boards contract. Solder joints weaken. Tiny differences in material expansion create stress that builds over time. A system that works flawlessly in a laboratory may behave unpredictably after weeks in near-freezing water. Failures are rarely dramatic. A sensor stops responding. A clock drifts out of sync. A power regulator becomes unstable. Individually, these problems seem minor. Together, they can end a mission. Batteries are particularly vulnerable. Chemical reactions slow dramatically at low temperatures. Capacity drops. Voltage becomes unreliable. Even specially designed cold-tolerant batteries lose efficiency. To compensate, engineers insulate battery compartments or use internal heaters, but both solutions consume energy. Energy is precious in an environment where resupply is impossible. Every watt used to keep a battery warm is a watt not used to collect data. Mechanical systems suffer in different ways. Lubricants thicken or solidify. Moving parts seize. Seals lose flexibility and begin to leak under pressure. Motors draw more power to overcome resistance, accelerating battery drain. In underwater vehicles, propellers must operate smoothly to maintain stability. A slight imbalance caused by ice crystals or material contraction can induce vibrations that interfere with sensors and navigation. Drift introduces another layer of difficulty. The ocean beneath the ice is not still, and neither is the ice itself. Autonomous vehicles navigating under ice must constantly adjust their position relative to a ceiling that moves independently of the water below. Without GPS signals, they rely on inertial navigation systems, acoustic beacons, and internal maps. Each method has limitations. Inertial systems accumulate error over time. Acoustic signals are distorted by ice and water layering. Maps become outdated as ice shifts. As a result, machines can lose track of where they are. A vehicle may believe it is beneath a safe recovery point, only to surface under solid ice kilometers away. Surfacing under ice is not a minor inconvenience. It can be fatal to the mission. Vehicles are designed to surface to transmit data, recharge, or be recovered. If they cannot find open water, they may exhaust their power searching, eventually shutting down. Drifting buoys face similar challenges. Once deployed, they move with the ice or currents. This movement is useful for tracking large-scale patterns, but it complicates long-term experiments. Instruments intended to sample a specific region may end up far from their original target. Over time, arrays spread out unevenly. Some drift into areas where recovery is impossible. Others are crushed as ice compresses. Tethers and cables often used to connect instruments to the surface introduce their own risks. Ice movement exerts unpredictable forces. A cable may be slack one moment and under extreme tension the next. Abrasion against ice edges weakens insulation. A single failure point can sever the connection entirely. Once disconnected, an instrument becomes autonomous whether it was designed to be or not. Freezing is not limited to temperature alone. Ice can physically encase equipment. Surface instruments left unattended can be buried by snow, locked in place by refreezing meltwater. Retrieval becomes impossible without heavy equipment, which may not be available or deployable in time. Even underwater instruments can become trapped if ice keels extend downward unexpectedly. Communication failures are common. Radio signals do not travel through seawater. Acoustic communication is slow and unreliable. Data transmission rates are low. Commands sent from the surface may be delayed or lost. Vehicles must make decisions independently based on pre-programmed logic. If conditions differ from expectations, those decisions may lead to unintended outcomes. This autonomy is both a strength and liability. Machines can operate without constant supervision, but they cannot improvise in the human sense. They do not recognize when a situation has changed in a meaningful but unanticipated way. A navigation algorithm may continue to follow a plan even as ice conditions deteriorate. By the time a problem is detected, it may be too late to intervene. Disappearance is the most unsettling outcome. Instruments are deployed with care, tracked as long as possible, and then simply stop responding. Sometimes the cause is known. A battery failed, a seal leaked, a cable snapped. Other times, the loss is silent. No final transmission, no clear explanation. The ocean keeps its secrets. These losses are not rare, they are expected. Budgets account for them. Engineers design redundancy into systems knowing some will never return. This acceptance reflects experience, but it also highlights how hostile the environment is. In few other places on Earth is the loss of expensive, carefully engineered equipment so routine. Recovery operations are constrained by time and conditions. Icebreakers are scarce and expensive. Weather windows are short. Helicopter operations depend on visibility and stable ice. Even when the location of a lost instrument is known approximately, reaching it may be impossible. The ice above may be too thick, too broken, or too unstable to support drilling or retrieval. This reality influences what questions scientists choose to ask. Experiments that require complex, fragile instruments are often avoided. Simpler measurements are favoured. This shapes the trajectory of research. Some phenomena remain understudied not because they are unimportant, but because studying them reliably is too risky. There is also a psychological toll. Teams invest years in designing, testing, and deploying equipment. Watching a mission fail due to factors beyond anyone's control is discouraging. Yet this is balanced by persistence. Each failure teaches something. Materials are improved, algorithms refined, designs adjusted. Progress is incremental. Machines that survive do so through careful compromise. They are built heavier than ideal to withstand pressure, more insulated than necessary to survive cold, more conservative in movement to avoid collisions. Each compromise reduces performance in some dimension. Speed decreases, sensor resolution drops, coverage shrinks. The result is a steady trade-off between survivability and capability. Even when machines work as intended, their presence alters the environment slightly. Thrusters stir sediment, lights attract organisms, noise propagates through water and ice. These disturbances must be accounted for in data interpretation. The machine is never a neutral observer. The phrase state-of-the-art takes on a different meaning here. Cutting-edge technology is often less reliable than simpler, well-tested systems. Innovation is cautious. Novelty is introduced slowly. In an environment where retrieval is uncertain, proven designs are valued over experimental ones. Despite all this, machines remain our primary means of exploration beneath the North Pole. They extend our reach into places we cannot go. They endure conditions we cannot survive. They gather data that would otherwise be impossible to obtain. but they do so imperfectly, under constant threat from cold, motion, and pressure. Understanding these limitations reframes the question of why exploration is incomplete. It is not a failure of imagination or effort. It is the result of sending machines into an environment that actively degrades them, moves them against their will, and occasionally claims them without explanation. As we continue, it becomes clear that even when machines survive freezing, drifting, and disappearance, they face another challenge that is less physical, but equally profound. They must operate in a place without reliable reference points, where maps lose meaning and orientation itself becomes uncertain. Imagine trying to navigate a place where every familiar cue has been erased. No horizon you can trust, no mountains in the distance, no coastline to follow, no fixed stars overhead for half the year. Even the ground beneath you refuses to stay put. This is the reality beneath the North Pole, a world where maps quickly lose relevance and landmarks simply do not exist in any stable sense. For exploration, this absence is not a poetic inconvenience. It is a fundamental problem that affects everything from navigation to data reliability, from safety planning to how knowledge itself is constructed. On land, maps work because land stays where it is. Roads, rivers, ridges and coastlines provide reference points that allow us to orient ourselves. Even when landscapes change slowly, the changes are small enough that maps remain useful for long periods. In most oceans, the surface serves a similar role. Ships navigate using GPS, stars, and known bathymetry. Even when currents move water around, the frame of reference remains stable. Under the ice at the North Pole, that frame collapses. The surface above the hidden ocean is in constant motion. Ice flows drift, rotate, compress, and fracture. A location marked on a map today may not exist tomorrow. The coordinates remain the same, but the physical reality attached to them does not. An instrument deployed at a specific latitude and longitude begins drifting the moment it touches the ice. Over weeks or months, it may travel hundreds of kilometers without ever leaving the ice it sits on. This drifting breaks a basic assumption of mapping, that a point corresponds to a place. Beneath the North Pole, a point corresponds only to a moment. Once that moment passes, the relationship dissolves. Any map that assumes permanence becomes, at best, a rough suggestion. Underwater, the problem intensifies. GPS signals do not penetrate seawater. Autonomous vehicles and instruments cannot know their absolute position without surfacing or receiving acoustic signals from known locations. But those known locations, often ice-based beacons or moorings, are drifting too. The reference frame itself is unstable. Inertial navigation systems help, but they are imperfect. They calculate position based on motion, acceleration, and orientation over time. Small errors accumulate. Over long missions, these errors grow. In open water, periodic GPS fixes correct them. Under ice, correction opportunities are rare. A vehicle may believe it knows where it is while slowly drifting further from reality. Acoustic navigation systems attempt to fill this gap. Beacons transmit sound signals that vehicles use to triangulate their position. But sound behaves unpredictably beneath ice. It reflects off the rough underside of floes. It bends as it passes through layers of water with different temperatures and salinities. Signals arrive distorted or delayed. Interpreting them requires assumptions that may not hold in changing conditions. Even the seafloor, which might seem like a stable reference, is less helpful than expected. Large-scale bathymetric maps of the Arctic Ocean exist, but they are incomplete and low resolution in many areas. Fine details remain unmapped. Under the North Pole, some regions have never been surveyed directly. Vehicles navigating close to the bottom cannot rely on detailed charts. Unexpected ridges or slopes can interfere with planned routes. Landmarks, in the usual sense, are absent. There are no visual markers to guide orientation, no consistent features that stand out across distances. The underside of ice varies from place to place, but those variations are subtle and transient. A ridge seen today may melt or shift tomorrow. A channel may close. What appears distinctive in one moment becomes generic in the next. This lack of landmarks affects not only navigation but also perception. Humans, even when operating through machines, rely on spatial memory. We remember where things are relative to other things. We build mental maps. Under the North Pole, those maps dissolve. Operators watch video feeds showing darkness punctuated by artificial light, with little sense of scale or direction. It becomes difficult to tell whether a vehicle is making progress or circling back on itself. Time compounds the problem. Because missions often last weeks or months, conditions change significantly between deployment and recovery. An area mapped early in a mission may look entirely different later. Ice thickness changes. Water properties shift. The environment does not preserve snapshots. It evolves continuously. This has consequences for data interpretation. When measurements are taken along a drifting path, separating spatial variation from temporal change becomes difficult. Did temperature change because the ocean warmed, or because the instrument moved into a different water mass? Did biological activity increase because conditions shifted, or because the instrument drifted into a more productive region? Without fixed reference points, these questions are hard to answer definitively. Scientists use statistical methods to untangle these effects, but uncertainty remains. The absence of stable landmarks introduces ambiguity that cannot be eliminated entirely. This ambiguity slows progress. Conclusions must be cautious. Claims must be qualified. Patterns emerge slowly through aggregation of many imperfect datasets. Safety planning is also affected. Emergency scenarios rely on known locations and predictable routes. Under drifting ice, escape paths are uncertain. An open lead identified earlier may have closed. A thin ice area may have thickened or fractured. Rescue operations depend on rapidly changing information. This increases risk for human crews and limits how far operations can push into uncertain territory. The psychological effect of operating without landmarks is subtle, but real. Disorientation increases cognitive load. Decision-making becomes more stressful. Operators must constantly monitor multiple data streams to maintain situational awareness. Fatigue sets in faster. Mistakes become more likely. In an environment where mistakes can be costly, this matters. Even defining success becomes harder. In many exploratory missions, success is tied to reaching a destination or mapping a region. Under the North Pole, destinations drift. Regions blur. Success becomes more about endurance, data continuity, and survival than about coverage or completion. This challenges how exploration is framed culturally. We're used to stories of discovery tied to places. A mountain climbed, a pole reached, a trench descended. The hidden ocean beneath the North Pole resists this narrative. There is no single place to arrive at, no landmark to photograph. Exploration here is process-based rather than place-based. Maps, when they exist, are dynamic. They incorporate uncertainty explicitly. They show probabilities rather than boundaries. They require constant updating. Even then, they lag behind reality. This makes planning iterative rather than definitive. Missions adapt in real time, adjusting goals as conditions evolve. Technology helps, but only partially. Advances in sensor fusion combine data from multiple sources to improve navigation estimates. Machine learning algorithms attempt to recognize patterns in noisy data. These tools reduce uncertainty but do not eliminate it. They operate within the same physical constraints. Without stable reference points, even the best algorithms must guess. There is also a philosophical implication. Much of scientific understanding relies on repeatability. Returning to the same place to observe change. Running experiments under controlled conditions. Under the North Pole, repeatability is elusive. You can return to the same coordinates, but not to the same place. Control is partial at best. This forces a shift in how knowledge is built. Instead of precise local understanding, researchers focus on broader patterns, trends over large areas, averages over time, statistical relationships rather than deterministic ones. This approach yields valuable insights, but it leaves gaps in fine-scale understanding. The absence of landmarks also affects how the hidden ocean is imagined by those who will never see it. Without clear images or defined places, it remains abstract. It is harder to care about a place that cannot be pictured. This influences public engagement and indirectly funding and attention. Yet this world without maps or landmarks is not empty. It is structured by forces that operate at scales and in ways that do not align with human intuition. Currents flow along invisible paths shaped by density and pressure. Ice kills sculpt the water beneath. Organisms navigate chemical gradients rather than visual cues. The environment makes sense to itself, even if it resists our frameworks. Understanding this helps explain why exploration beneath the North Pole advances slowly and unevenly. It is not just about overcoming cold, pressure, or darkness. It is about letting go of expectations shaped by environments that offer orientation and stability. It is about accepting that some places cannot be neatly mapped or easily revisited. As we move forward, this lack of maps and landmarks sets the stage for another challenge. Even when we manage to navigate, even when machines survive and data is collected, the things we seek to understand, especially life itself, remain elusive. Detection becomes indirect. Presence becomes inferred rather than observed. And the ocean keeps much of its story just beyond our grasp. When people imagine life in the ocean, they often picture abundance that announces itself clearly. Schools of fish moving in coordinated flashes, large animals breaking the surface, coral reefs visible from above in shallow water. Even in the deep sea, popular imagination tends to focus on strange but visually striking creatures illuminated briefly by submersible lights. Beneath the North Pole, life exists very differently. It does not advertise itself. It does not rely on visibility. And it does not make itself easy to find, even when scientists know it must be there. The first difficulty begins with expectation. For a long time, the Central Arctic Ocean was assumed to be biologically sparse, almost empty compared to more temperate seas. Thick ice block sunlight, cold slows metabolism, nutrients are thought to be limited. From a surface perspective, this seemed reasonable. Less light should mean less photosynthesis. Less energy should mean fewer organisms. But over time, this assumption has proven incomplete. Life is present beneath the ice, not in obvious concentrations, but in forms adapted to conditions that challenge almost every standard method of detection. Much of this life is small, microscopic, planktonic, bacterial. These organisms do not form reefs or schools that can be spotted by cameras. They exist suspended in the water column or attached to the underside of ice. Their presence is often inferred from chemical signatures rather than seen directly. A slight change in oxygen concentration, a trace of organic carbon, a fragment of genetic material drifting past a sensor. Each hint suggests activity, but none provide a full picture. The underside of sea ice itself hosts a complex ecosystem. Algae grow in tiny channels and pores within the ice, using the limited light that filters through snow and ice above. These algae form the base of a food web that supports small invertebrates, which in turn support larger organisms. This entire system exists upside down compared to what we usually imagine, clinging to ice rather than growing upward from the sea floor. Studying this underside community is extraordinarily difficult. Access requires drilling through ice that may be several meters thick, in conditions where cracks can form unexpectedly. Once a hole is opened, it begins to refreeze immediately. Equipment must be deployed quickly. Sampling disturbs the environment. Artificial light alters behavior. What is observed is always a partial, fleeting glimpse. Below the ice-associated life, the water column hosts organisms adapted to darkness. Some migrate vertically, moving up and down in response to subtle cues. Others remain at specific depths, where temperature and salinity create favourable conditions. Many are gelatinous, fragile, easily destroyed by nets or pumps used to collect samples. By the time they reach the surface, they may be unrecognisable. Pressure changes during retrieval add another problem. Organisms adapted to high pressure do not tolerate decompression well. Cells rupture. Enzymes fail. What arrives in the laboratory may bear little resemblance to what existed at depth. This makes classification difficult and behaviour almost impossible to study. Observations are reduced to static snapshots of damaged specimens. Cameras offer limited help. Light attracts some organisms and repels others. Many Arctic species have evolved to avoid light entirely. They sense vibrations, chemical gradients, or pressure changes instead. A vehicle approaching with lights and thrusters creates an artificial disturbance field. The scene captured on camera may represent a reaction, not normal behaviour. Acoustic methods, useful for detecting larger animals in other oceans, are less effective here. Many Arctic organisms are small and do not reflect sound strongly. Others live close to the ice or seafloor, where acoustic clutter makes interpretation difficult. Ice itself produces noise as it cracks and moves, masking biological signals. Even when life is detected, understanding its role is challenging. Metabolic rates are slow. Interactions unfold over long time scales. Seasonal cycles dominate behaviour. A snapshot taken during one expedition may not represent conditions weeks later. Long-term observation would help, but maintaining instruments in place long enough to observe these cycles is extremely difficult under drifting ice. There is also the issue of patchiness. Life beneath the North Pole is not evenly distributed. Small differences in ice thickness, light penetration, or nutrient availability can create localized hotspots of activity, surrounded by relative emptiness. Instruments drifting through this environment may miss these hotspots entirely, or sample them briefly without context. Data becomes noisy, variable, and hard to generalize. Genetic techniques have expanded what can be detected. Environmental DNA allows scientists to identify organisms based on genetic fragments in the water. This has revealed surprising diversity beneath the ice. But DNA tells us presence, not abundance or activity. It cannot distinguish between a thriving population and a few transient individuals carried by currents. Interpretation requires caution. Higher up the food web, larger organisms exist, but they are sparse and wide-ranging. Fish, seals, and other mammals move through the Arctic Ocean following ice conditions and prey availability. Their paths are difficult to track. Tagging animals requires close contact, which is logistically challenging and ethically constrained. Once tagged, data transmission is limited by ice cover and battery life. Predators beneath the ice operate in a three-dimensional environment shaped by ice keels and water layers. Their behaviour does not align with surface geography. A seal may hunt along the underside of ice ridges invisible from above. A fish may follow a temperature gradient rather than a horizontal route. Understanding these patterns requires integrating biological data with physical oceanography, but both datasets are incomplete. The difficulty of studying life here also affects how research questions are framed. Scientists often focus on what can be measured reliably, such as chemical cycles or physical properties. Biological questions become secondary, not because they are less important, but because they are hard to answer with confidence. This creates gaps in understanding that persist despite decades of effort. There is also the challenge of change. As the Arctic warms, ice cover thins and retreats. Light penetration increases in some areas. New species move northward. Existing species adapt or decline. These changes are happening faster than our ability to document baseline conditions. Without a clear picture of what life looked like before, assessing impact becomes difficult. This uncertainty has consequences beyond science. Arctic ecosystems influence global processes, including carbon cycling and climate feedbacks. Microbial activity affects how carbon is stored or released. Changes in food webs influence higher predators and indigenous communities that rely on them. When life is hard to detect, its importance can be underestimated. The hidden nature of this life also affects public awareness. It is easier to care about visible animals than microscopic communities. It is easier to respond to dramatic images than subtle shifts in chemical balance. The life beneath the North Pole does not lend itself to simple narratives. It exists quietly, persistently, without spectacle. Yet this quiet persistence is precisely what makes it important. These organisms have adapted to some of the most challenging conditions on Earth. They represent evolutionary solutions to darkness, cold, and scarcity. They form systems that function efficiently without drawing attention. Ignoring them because they are hard to study would be a mistake. Efforts to improve detection continue. New sensors aim to measure metabolic activity directly. Autonomous platforms are being designed to observe without disturbing. Pressure-retaining samplers are being refined. Each advance brings incremental improvement, not sudden revelation. Progress is slow, but it is real. Still, even with better tools, life beneath the North Pole will likely remain partially hidden. Not because of negligence, but because the environment favours subtlety. It rewards organisms that blend in, that operate below thresholds of detection. Our instruments, like our senses, evolved for different conditions. Understanding this helps explain why exploration here feels incomplete. It is not just that the ocean is hard to reach, it is that the life within it does not reveal itself easily. Detection is indirect. Study is constrained. Knowledge accumulates slowly, piece by piece. As we continue, this difficulty in observing life connects to a broader theme. Human limitations are not only technological, they are physiological, psychological, and logistical. The environment beneath the North Pole does not accommodate prolonged human presence, and that, more than any single obstacle, shapes what we can and cannot know. For all the technology we build and all the data we gather, exploration ultimately begins and ends with human capacity. Machines are designed, deployed, monitored, and interpreted by people. Decisions are made by human minds. Risks are weighed by human judgment. And in the environment beneath the North Pole, those human limits become impossible to ignore. This is not a place that bends easily to endurance, adaptability, or resilience. It is a place that steadily exposes where those qualities thin out. Cold is the most obvious constraint, but its effects are often misunderstood. Extreme cold does not simply make things uncomfortable. It alters how the body functions at a fundamental level. Blood vessels constrict to preserve core heat. Fine motor control degrades. Reaction times slow. Decision-making becomes more conservative, or paradoxically more error-prone. Tasks that are trivial in mild conditions take significantly longer. Every exposed moment carries a cumulative cost. Even with modern protective clothing, cold works its way in. Gloves reduce dexterity. Face coverings limit visibility and communication. Layers restrict movement. Fatigue arrives sooner because the body expends more energy simply maintaining temperature. Sleep becomes lighter and less restorative. Over days or weeks, this background strain compounds, quietly eroding performance. Psychologically, the environment exerts pressure as well. Isolation is profound. The Central Arctic offers no visual variety, no natural landmarks to break monotony. White and grey dominate the landscape. During polar night, darkness persists around the clock. The absence of natural day-night cues disrupts circadian rhythms, affecting mood, alertness, and sleep quality. Even experienced personnel report disorientation and irritability after extended exposure. The sense of risk is constant. Ice can crack without warning. Weather can change rapidly. Evacuation options are limited. Every movement outside a secure shelter requires planning and vigilance. This sustained alertness is exhausting. Unlike acute danger, which triggers adrenaline and focus, chronic risk wears people down gradually. Human error becomes more likely under these conditions. Small mistakes, miscommunications, lapses in attention can have outsized consequences. A dropped tool becomes irretrievable. A misjudged step leads to injury far from medical facilities. A delayed response to changing ice conditions forces evacuation. The margin for recovery is narrow. Logistics amplify these limits. Everything required for an expedition must be transported over vast distances. Fuel, food, equipment, spare parts, medical supplies, all must be planned months in advance. Resupply is rarely possible. If something essential fails or runs out, improvisation options are limited. This requires conservative planning, which in turn limits flexibility and ambition. Medical considerations impose further constraints. Cold-related injuries such as frostbite and hypothermia are ever-present risks. Even minor injuries can become serious when healing is slowed by cold and stress. Evacuating an injured person from the Central Arctic can take days, depending on weather and ice conditions. This reality influences how tasks are assigned and how long operations can safely continue. Team dynamics matter more in isolation. Small groups work together in confined spaces for extended periods. Tensions that might be manageable elsewhere can escalate. Psychological support becomes as important as physical safety. Selection and training emphasize not only technical skills but emotional resilience and cooperation. The cold also affects cognition in subtle ways. Studies show that prolonged exposure to low temperatures can impair memory, attention, and problem solving. These effects may not be immediately obvious, but they influence complex tasks like interpreting data, troubleshooting equipment, or making strategic decisions. In an environment where mistakes are costly, even small cognitive shifts matter. Human presence beneath the ice itself is essentially impossible. Unlike shallow water research, there is no option for direct human observation. No divers, no hands-on interaction. Everything must be mediated through machines, which adds layers of abstraction. Scientists cannot feel currents, see organisms directly, or respond intuitively to unexpected conditions. They must rely on screens, numbers, and delayed feedback. This distance affects understanding. Direct experience often reveals patterns that data alone cannot. In the Arctic, that experiential layer is missing. Researchers compensate with training and simulation, but there is no true substitute. The environment remains conceptual rather than felt. Time limits are imposed by both environment and physiology. Expeditions are short. Field seasons are narrow. The body can only tolerate extended exposure for so long before risk outweighs benefit. This limits the duration of experiments and the continuity of observation. Long-term presence, common in other research settings, is rare here. There is also the issue of aging infrastructure and expertise. Polar research requires specialized skills that take years to develop. Fewer people are trained for this work. As experienced personnel retire, replacing that knowledge takes time. The pool of individuals capable of operating effectively in such conditions remains small. Cultural and ethical considerations further shape human limits. Indigenous knowledge provides valuable insights into Arctic environments, but the central Arctic Ocean beneath the North Pole lies far from traditional habitation. Human experience there is limited historically as well as practically. Ethical concerns about risk, environmental impact, and resource allocation influence how aggressively exploration is pursued. These human limits do not represent failure, they represent boundaries. Recognizing them is essential for responsible exploration. Pushing beyond them recklessly would increase risk without guaranteeing understanding. The environment does not reward bravado, it rewards caution, patience, and humility. This recognition shapes the pace of discovery. Progress is measured, deliberate. Questions are prioritized. Methods are tested incrementally. There are no shortcuts that bypass human constraints without introducing unacceptable risk. This frustrates expectations formed in an age of rapid technological advancement, but it reflects reality. Understanding human limits also reframes the narrative of exploration. It shifts focus away from conquest and toward coexistence with constraints. The goal becomes not to dominate the environment, but to learn within its terms. This approach yields slower results, but more reliable ones. As we approach the final layers of this exploration, these human boundaries connect to a deeper uncertainty. Even if we could endure longer, deploy better machines, and gather more data, the ocean beneath the North Pole may still hold things back. Not because of hostility, but because complexity itself resists complete understanding, and that lingering uncertainty invites a final reflection on what remains unseen and perhaps unknowable beneath the ice. Even after accounting for ice that never rests, pressure that crushes without warning, machines that fail quietly, and human limits that cannot be negotiated, there remains a deeper layer to this question. It is the possibility that the ocean beneath the North Pole is not merely unexplored because it is difficult, but because it contains processes, structures, and interactions that do not reveal themselves easily, even when we look in the right direction. Some things are hidden not by distance or darkness alone, but by complexity. The Arctic Ocean beneath the North Pole is not a static container of water. It is a system in constant negotiation with itself. Heat enters from lower latitudes and becomes trapped beneath colder layers. Fresh water from melting ice alters density and circulation. Salinity gradients shift slowly, sometimes abruptly. These processes interact in ways that are difficult to isolate. When scientists measure one variable, they often influence or miss another. This system responds not linearly, but conditionally. One of the most significant unknowns lies in how heat is stored and released beneath the ice. We know that warm Atlantic water flows into the Arctic and sinks below fresher surface layers. We know this heat contributes to ice loss from below. What we do not fully understand is how this heat moves once it is there. Does it remain trapped for long periods, slowly eroding ice? Does it rise episodically in bursts? Does it circulate laterally in ways we have not mapped? Small differences in these mechanisms could have large implications for future ice stability. Another uncertainty involves mixing. Vertical mixing in the Arctic Ocean is limited by strong stratification, but it does occur. Storms, internal waves, and interactions with ice keels can disrupt layers temporarily. These events are difficult to observe directly and may happen infrequently. Yet, they could play an outsized role in redistributing heat, nutrients, and gases. If such mixing events are more common or more intense than we realize, our models may underestimate their impact. The chemistry of the hidden ocean also holds unanswered questions. Carbon cycling beneath the ice is poorly constrained. We know the Arctic plays a role in absorbing atmospheric carbon dioxide, but how that carbon moves through the system remains uncertain. Microbial communities process carbon in ways that are sensitive to temperature, pressure, and nutrient availability. Changes in any of these could shift the balance between storage and release, influencing global climate feedbacks. Methane is another area of uncertainty. Arctic sediments contain methane hydrates, ice-like structures that trap methane under pressure. Warming and pressure changes could destabilize these hydrates, releasing methane into the water column. Whether this methane reaches the atmosphere, is consumed by microbes, or remains trapped is not fully understood. The hidden ocean may be moderating these processes quietly, buffering or amplifying change in ways we have yet to detect. Biologically, there may be entire communities we have not observed directly. Life adapted to extreme cold, darkness, and pressure may operate on timescales and metabolic pathways unfamiliar to us. Slow growth, long lifespans, and subtle interactions make detection difficult. Some organisms may exist at densities below current detection thresholds. Others may occupy niches we do not sample because we do not know to look there. There is also the question of connectivity. How isolated is the central Arctic Ocean biologically? Do organisms migrate between it and other oceans more freely than assumed? Or are there barriers that create unique evolutionary pathways? Genetic studies hint at both isolation and connection, but the picture is incomplete. The hidden ocean may be a crossroads, a refuge, or both, depending on species and conditions. Physical structures beneath the ice may also surprise us. The underside of sea ice is not smooth. It contains ridges, cavities, and channels that influence water flow and habitat availability. At greater depths, seafloor features remain poorly mapped. Subtle topography can steer currents, create upwelling zones, or trap organic matter. Without detailed maps, these influences remain speculative. Temporal change adds another layer of uncertainty. The Arctic is changing rapidly. Conditions observed today may not reflect those of a decade ago, let alone historical baselines. Without long-term records, distinguishing natural variability from anthropogenic change is challenging. The hidden ocean may be undergoing transitions that we are only beginning to glimpse, their significance unclear until much later. There is also the possibility of emergent behaviour. Complex systems sometimes exhibit properties that cannot be predicted from their components alone. Feedback loops can stabilise or destabilise conditions unexpectedly. Thresholds may exist beyond which change accelerates. The hidden ocean, with its layered structure and interacting processes, may harbour such thresholds. Identifying them requires comprehensive understanding that remains out of reach. Some uncertainties are methodological. Our instruments measure what they are designed to measure. Variables outside those parameters remain invisible. If important processes operate through mechanisms we have not prioritized, they may go unnoticed. History offers many examples of scientific blind spots, revealed only after new tools or perspectives emerged. There is also the matter of scale. Processes that seem insignificant locally may matter globally when aggregated. Conversely, dramatic local events may average out over larger regions. Without adequate spatial coverage, it is difficult to know which is which. The hidden ocean's vastness magnifies this problem. The question of what remains hidden is not a failure of curiosity. It is an acknowledgement that knowledge has limits shaped by access, tools, and interpretation. Some aspects of the ocean may remain partially unknown, even with sustained effort. This does not diminish their importance. It highlights the need for humility in how conclusions are drawn. Importantly, uncertainty does not imply emptiness. The hidden ocean is active, responsive, and interconnected. It influences ice above, atmosphere beyond, and oceans elsewhere. What it keeps from us is not necessarily secrets in the dramatic sense, but nuance, gradients rather than binaries, processes rather than events. This perspective challenges how exploration is often framed. Discovery is not always about uncovering something entirely new. It can be about realizing how much complexity lies beneath what we thought we understood. The Arctic Ocean, beneath the North Pole, may not reveal a single defining mystery, but many subtle ones whose significance emerges slowly. As we move toward the final part of this journey, this lingering uncertainty becomes central. It reminds us that exploration is not only about reaching places, but about accepting that some places do not yield easily to complete understanding. And that acceptance shapes how we choose to look, what we value in the data we do have, and how we relate to the unseen processes shaping our world. There is a moment that arrives quietly when you've traced every obstacle, examined every limitation, and followed every thread of difficulty as far as it will go. It's the moment where the question shifts, not from curiosity to certainty, but from effort to perspective. Standing at the edge of the unseen beneath the North Pole is not about reaching a final answer. It is about recognizing where our reach ends and where the ocean continues without us. By this point, it becomes clear that the hidden ocean is not inaccessible because we have failed to try hard enough. It remains out of full reach because it exists at the intersection of forces that do not scale to human convenience. Cold that dulls reaction and drains energy. Ice that refuses to stay still long enough to trust. Darkness that strips away the most basic sense we rely on for understanding. Pressure that compresses matter and patience alike. Machines that do their best and then quietly stop responding. And people who, no matter how trained or determined, remain bound to fragile bodies and finite endurance. What emerges from this is not a story of defeat, but of proportion. The Arctic Ocean beneath the North Pole is not small, it is not marginal, it is vast, layered, and deeply integrated into the planet's systems. Our presence within it is narrow by comparison, temporary, mediated, partial. We touch it lightly, briefly, and often indirectly. This perspective changes the emotional tone of exploration. It moves away from urgency and toward attentiveness. The goal is no longer to reveal everything, but to listen carefully to what does reveal itself. A temperature profile here, a chemical signal there, a drifting instrument that returns after months with a quiet record of what it encountered. Each piece matters, not because it completes the picture, but because it sharpens the edges of what remains unseen. Standing at this edge also reframes uncertainty. In many contexts, uncertainty is treated as a problem to be eliminated. Here, it becomes a feature of the environment itself. The hidden ocean does not present itself cleanly. It changes faster than we can anchor ourselves to it. It responds to forces operating far beyond local scales. Accepting this uncertainty is not resignation, it is realism. There is also something instructive about the way this ocean resists mapping and mastery. In an era where much of the planet feels increasingly measured, tracked and quantified, the central Arctic remains stubbornly opaque, not because it is untouched, but because it cannot be reduced easily. It reminds us that knowledge does not always arrive as clarity. Sometimes it arrives as restraint. This restraint influences how science proceeds here. Questions are framed carefully, claims are hedged, conclusions are provisional, progress is cumulative rather than spectacular. A decade of work may yield a refinement rather than a revelation. From the outside, this can appear slow. From within, it feels appropriate. The edge of the unseen is also where imagination must be disciplined. It is tempting to fill gaps with assumptions, to extend patterns observed elsewhere, to project familiar dynamics onto unfamiliar systems. But the Arctic Ocean beneath the North Pole has already demonstrated how unreliable those projections can be. It behaves according to its own constraints, shaped by geography, physics, and history that do not align neatly with more accessible regions. Looking down into this unseen space also reveals how interconnected absence can be. The lack of direct observation affects models. Models influence forecasts. Forecasts shape policy and public understanding. When something remains hidden, its influence does not disappear. It simply becomes harder to account for accurately. This makes careful, conservative interpretation essential. There is a quiet humility required here. Not the performative kind, but the practical kind that accepts limits without romanticizing them. The ocean does not owe us transparency. It does not exist to be understood on our schedule. It operates continuously, whether observed or not. At the same time, standing at this edge does not mean stepping back entirely. It means choosing where to lean forward. Targeted questions, focused measurements, incremental improvements in tools and methods. Each expedition adds texture rather than resolution. Over time, those textures accumulate into something resembling understanding, even if sharp outlines never fully emerge. There is also continuity in this position. The edge is not static. As ice thins or thickens, as technology advances, as climate alters baseline conditions, the boundary between known and unknown shifts. What was unreachable decades ago becomes marginally accessible. What was assumed stable becomes questionable. The unseen does not retreat, it rearranges. For those who work in this environment, this becomes familiar. The sense that you're always approaching, never arriving, that each answer generates a new layer of questions, that the most important realization is often how much context matters. Measurements divorced from their environmental conditions lose meaning quickly here. This way of knowing contrasts sharply with how exploration is often portrayed. There is no single moment of arrival, no definitive map unfurled, no final image that explains everything. Instead, there is persistence, patience, and a willingness to work with fragments. Standing at the edge of the unseen also invites a broader reflection. The Arctic Ocean beneath the North Pole is not unique in resisting complete understanding. It is simply one of the few places where that resistance remains obvious. In many other systems, complexity is hidden beneath apparent clarity. Here, complexity announces itself through difficulty. This difficulty is not an invitation to abandon inquiry. It is an invitation to recalibrate expectations, to value long-term observation over immediate insight, to accept that some systems are better understood statistically than narratively, to recognize that knowledge can be provisional without being weak. As you picture this ocean now, not as a blank space, but as an active, layered system moving quietly beneath drifting ice, it becomes easier to appreciate why exploration here unfolds the way it does. Not because of a lack of effort, but because the environment sets boundaries that cannot be ignored. And so we remain at this edge, looking down, not with frustration, but with attentiveness, acknowledging what we know, what we suspect, and what remains unresolved. The hidden ocean continues its work beneath the ice, shaping climate, sustaining life, redistributing heat, indifferent to whether it is fully seen. Somewhere above it, instruments drift. Data accumulates slowly. People plan the next cautious step. The unseen does not vanish. It waits, not to be conquered, but to be approached again, carefully, on terms that are never entirely our own.